Grab your air guitar and get ready to jam because the Rockin' World of Geology Program 4 is going to examine the two different kinds of rock. First, we'll check out sedimentary rock, starting with how it's formed and what it's made of. We'll even look at different kinds of sedimentary rock. But that's not the only rock you'll find in the standard deviance quarry. You'll also get the skinny on metamorphic rock.
Pop quiz time! Which of the following is not a primary cause of metamorphism in rocks? A. Evaporation. B. Heat. C. Pressure. D. Fluids. Think you know? Stay tuned and we'll give you the answer after the show.
The Standard Deviants present The Rockin' World of Geology.
Starring Brad Aldous, Galila Azrez, Herschel Bliefeld, Jeremy Clavens, Tessa Monroe, Dina Rubinson, Gabrielle Smith, Malcolm Smith, Shannon Ward, and Jazz Mastin. Section F, Sedimentation and Sedimentary Rocks.
We talked a little bit about sedimentary rocks earlier. We'll go into more detail about them now. The word sedimentary comes from the Latin word sedimentum, which means settling. Sedimentum literally refers to a solid material settling out of liquid, which is the way most sedimentary rocks are originally deposited. Little weathered pieces of existing rocks, which we'll call sediment, erode and are deposited in valleys, seas, lakes, and most importantly, the ocean. As more and more sediment gets deposited, the earlier layers of the sediment get buried and compacted together. Eventually, due to the pressure of burial, the deep sediment is cemented together, forming solid rocks.
Why don't you go ahead and do this one?
Okay, sure. Sedimentary rocks are an important part of the rock cycle. Do you know what the rock cycle is?
It's a prehistoric exercise device.
No. The rock cycle shows the interrelationship of the three fundamental rock types and explains the existence and formation of each. The three fundamental rock types are sedimentary, which we just went over, igneous, the rocks that form from cooling lava or magma,
Igneous.
and metamorphic. Metamorphic rocks form from sedimentary or igneous rocks that are altered by heat and pressure, and sometimes by chemical reactions. Here's how the rock cycle works. Igneous rocks that are not buried beneath the surface will weather, erode, and form sediments. Those sediments accumulate in deposits that pile up on each other and get cemented together to form solid sedimentary rocks. The solid sedimentary rocks are composed of little pieces of weathered and eroded igneous rocks. Then, the sedimentary rocks are often buried and subjected to metamorphic processes, such as intense pressure, heat, and possibly chemical reactions. The metamorphic processes change the sedimentary rocks, making them into metamorphic rocks. Upon exposure to even higher temperatures, these metamorphic rocks can then melt back into magma. The magma cools, forms igneous rocks, and the rock cycle starts over again. Pretty cool, huh?
Now that you understand the rock cycle, let's go into some more detail about sedimentary rocks. The sediment in sedimentary rocks is solid rock particles produced by weathering igneous rocks. These particles are called clastic materials, and the accumulation of clastic materials is called clastic sediment.
Paper or clastic?
Clastic sedimentary rocks are classified by the grain sizes of their component clastic materials. There are three general categories of sedimentary rocks: conglomerates, sandstones, and mudstones. Mudstones can be further subdivided into siltstone and shale.
Sedimentary rocks, composed of large clastic sediments, are called conglomerate sedimentary rocks. The large sediments that make up conglomerates include boulders, cobbles, pebbles, and granules. Each of these sediment types is larger than 2 millimeters in diameter.
Smaller clastic sediments between 2 millimeters and 1/16 millimeters are called sand. Sedimentary rocks made up of sand are logically enough called sandstone.
Sedimentary rocks made of clowns are called clownstone.
The third type of sedimentary rocks are made of clastic sediments that are smaller than 1/16 of a millimeter in diameter. These tiny sediments are called silt and clay. Sedimentary rocks made up of silt are called siltstone. Silt is sediment that's between 1/16 and 1/256 of a millimeter in diameter. Shale is a sedimentary rock composed of clay-sized particles. Clay is sediment which is smaller than 1/256 of a millimeter. Mudstones are composed of both silt and clay in approximately equal proportions.
You can tell a bit about the environment in which sedimentary rocks formed by the size of the component sediments. You know how sediments are moved around mostly by water. Now, it takes a lot more energy to move big stones than small ones, right?
Yeah.
Okay, so in other words, a big, fast-moving river might be able to carry a good-sized rock, but a slow little trickle can only carry tiny sediments like silt. See, siltstone can form around stagnant lagoons, where there's not a fast, energetic current carrying in large particles to add to the bed of sediments.
Because the sluggish water only brings in tiny sediments, right?
Right. Conglomerates, though, which are composed of large clastic sediments, form near sources of higher energy, like fast-moving rivers that can carry large sediments along for some distance before they settle out and collect in deposits.
Now let's talk about chemical sedimentary rocks. You know from the rock cycle that sedimentary rocks form from the weathered remains of other rocks. Sedimentary rocks also form from materials produced by weathering seashells and other components of the environment that break down. Weathering rocks and seashells and stuff produce salts and ions that dissolve and wash into lakes and oceans. If these dissolved salts and ions later precipitate or separate back out of the solution they formed with the water, they can form mineral particles. These particles accumulate as chemical sediments, eventually forming what we call chemical sedimentary rocks.
Unlike clastic sedimentary rocks, which are classified by the size of their component particles, chemical sedimentary rocks are classified by their chemical composition. For example, carbonate rocks are chemical sedimentary rocks which are made up primarily of calcium carbonate, or CaCO3. Limestone is a carbonate rock composed of pure calcium carbonate.
Limestone.
Hey, what about chalk?
Little pieces of chalk!
Yeah, okay, chalk too.
The next type of sedimentary rocks is evaporites. It's easy to remember how evaporites form. Evaporating seawater leaves behind deposits which lithify or harden into sedimentary rocks. Seawater evaporates to form evaporites. Common evaporites are halite, which is also called sodium chloride or rock salt, and gypsum, which forms from evaporating solutions containing calcium sulfate.
Coal is a biochemical sedimentary rock. It's called biochemical because it forms from organic sedimentation, which is the weathering remains of plants and animals. The partially decomposed organic crud, called peat, accumulates and is eventually buried and transformed into rock.
The environment in which rocks form is called the paleoenvironment. Some important paleoenvironments where sedimentary rocks form are
In and around rivers, these are called fluvial environments. Deltaic environments, which, like the Mississippi Delta, are fan-shaped deposit areas at the mouths of rivers, desert environments, shallow marine environments, lacustrine environments, which are stagnant lagoons and lakes, beach environments, turbidite environments, which are deposits on underwater marine slopes, and pelagic environments, where you find open ocean sediments.
So, you know that the materials that make up sedimentary rocks are deposited in layers, and these layers might differ from one another in composition. When the layers of materials lithify or solidify into rocks, the rocks also have layers that look like stripes, which are called bedding or stratification. You can tell a lot about a sedimentary rock's paleoenvironment by looking at the rock stratification. You know, the stripes.
Layers which are inclined at an angle to the main bedding planes are called cross-bedding. Cross-bedding indicates that wind or water deposited the sediment. The cross-beds incline downward in the direction of the flow of wind or water because the wind or water push the sediments in that direction.
Ripple marks are low, narrow ridges preserved on sedimentary rocks, generally sandstones, which look like a rippled water surface. You can tell by looking at the ripple marks whether the rock formed in water where the current moved in one direction or in water where the waves moved to and fro.
Graded bedding is bedding in which the size of the clastic sediments changes. For example, the clasts in a stratified or layered sedimentary rock might go from cobble-sized at the bottom to fine-grained sand at the top. Graded bedding indicates that the energy in the environment where the rock formed changed over time. For example, a stream might be fast-moving and leave deposits of large cobbles in a bed. Then, over time, its current gets weaker, and the size of the clastic material deposited by the stream gets smaller and smaller. The energy of the stream isn't strong enough to carry large sediments anymore.
Evidence of mud cracks in sedimentary rocks also tells you something about the environment in which they were formed. Mud cracks form in clay-rich sediment that dries out. If you see preserved polygonal-shaped mud cracks in sedimentary rock, you know that the rock formed in an area like the floodplain of a river that dries out periodically.
Sedimentary facies are the characteristic physical and chemical attributes a sedimentary rock gets from its environment. Think of the term facies like characteristics. The rock's visible shape and internal components that can be attributed to the environment in which it was formed are called its facies. For example, a process called marine transgression affects the facies or physical and chemical characteristics of the sedimentary rocks forming on the seashore.
Marine transgression occurs when the sea covers land on a continent that used to be exposed to the air. In other words, the shoreline is moving inland, covering more of the land. Bummer for humans, cool for fish. Marine transgression covers sediments that were deposited on dry land with sediments that were carried by the sea. The sediments carried by the sea are different from the sediments that get deposited on land. This difference shows up in the facies, or internal and external characteristics, of the sedimentary rocks that form in areas of marine transgression.
All of my rocks have smiley faces on them.
Marine regression is the opposite of marine transgression. The shoreline moves further out, so more land is exposed. The effects of marine regression also show up in the composition of the layers of sedimentary rocks formed in the area. The sediments that were deposited by the sea are covered by sediments deposited on dry land. The sedimentary facies reflect this change in sediment composition.
Keep in mind that there's no single indicator that will tell you beyond the shadow of a doubt where or how a rock was formed. Geologists rely on a combination of clues and sources for answers.
Part 1, Metamorphism. Section A, Causes of Metamorphism.
Deep in the Earth's crust, it gets hot. And when it gets that hot, you have to have a party!
That was fun, but back to the point. Sometimes it's so hot and the pressure is so enormous in the Earth's crust that the rocks melt into magma. When it's not hot enough to melt the rocks, the heat and pressure is still often great enough to cause the rocks to change their mineral composition and crystalline textures and become a new type of rock. When rocks undergo these changes, we say they are metamorphosed. Yes, folks, we're about to tell you about the next big category of rocks, metamorphic rocks.
I'm so hot. I can't stand the pressure. I don't even know who I am anymore.
By providing energy, heat speeds up chemical reactions, such as the breaking of chemical bonds and the altering of crystal structure. Rocks exposed to lots of heat will often metamorphose into rocks that are more stable at high temperatures. In other words, rocks exposed to high temperatures will sometimes change their composition until they take on a form that can withstand the heat.
Pressure is another factor in metamorphism. Buried rocks are subjected to pressure from the weight of all the rocks on top of them. The deeper they are buried, the more stress they are subject to. The mineral grains in a buried rock may pack more closely together, or actually recrystallize as a result of pressure. The recrystallized rocks may have the same chemical compositions as the rocks they form from, or exposure to pressure may cause a change in their chemical composition.
The presence of fluids, such as water, is another factor influencing the formation of metamorphic rocks. Like heat, the presence of a fluid can increase the rate of metamorphic reactions. Water and carbon dioxide are usually present in areas where metamorphism is occurring. The water may contain ions that move freely through the water and speed up the rate of chemical reactions acting on the rocks.
There's one more little-known factor influencing the formation of metamorphic rocks, and that's peer pressure. No, actually, it's true. Rocks are more likely to change their appearance and composition if all the rocks around them are doing the same thing.
Section B, types of metamorphism.
There are different types of metamorphism. We distinguish one from another by the cause of the metamorphism. Two types of metamorphism are contact metamorphism and regional metamorphism.
Metamorphism caused by hot magma intruding into an existing rock is called contact metamorphism. We'll explain.
Plutons form when hot magma intrudes into a bed of existing rock. When plutons form, contact metamorphism may occur. The intruding magma heats up and stresses the existing country rock.
During contact metamorphism, the hot magma comes into contact with the country rock, and the heat from the intruding magma causes the country rock to metamorphose. The part of the country rock that metamorphoses as a result of contact with the magma is referred to as an areole.
Regional metamorphism occurs when high pressures and temperatures affect huge areas of the Earth's crust. Large-scale regional metamorphism occurs when tectonic plates, remember those continent-sized chunks of crust we talked about earlier, bump against each other. As you might imagine, the friction and stress of two whole continents crunching against each other can cause huge regions of rock to metamorphose.
What actually happens to metamorphic rocks when the heat and pressure gets a hold of them?
Well, we mentioned that the actual composition and crystal structure of the minerals can change in response to heat and pressure. When the basic composition and structure change, the rocks actually change their identity and they even get new names. For example, shale can turn into slate, a considerably harder rock, when it's an environment that's about 200 degrees Celsius.
Every rock has got a name. We got Tony, we got Frankie, we got Stevie, we got Ron, we got...
Naturally, metamorphosed rocks are likely to look and feel different than they did before they changed. There's a set of attributes and textures that metamorphosed rocks commonly exhibit, and these particular attributes and textures all have names, of course.
And you're going to give us more terms, right?
Yes, I am.
And we're going to have to learn them, right?
Yes, you are.
Ugh.
What? What's the problem? Don't you want to know what schistosity is?
Heat and pressure can cause a general metamorphic characteristic called foliation. The pressure that's applied to rocks undergoing metamorphism sometimes pushes the minerals into a parallel pattern. The parallel pattern that forms when the minerals align themselves in flat or wavy parallel planes is called foliation. Foliation produces a texture that is especially apparent along cleavage planes where the rock is split. You can see foliation and you can feel it. You can't smell foliation, so don't try.
Do these terms apply to any other kind of rock besides metamorphic?
Nope, only metamorphic.
So, foliation is a texture caused by the alignment of minerals into parallel bands. There are 3 specific types of foliation: slaty cleavage, schistosity, and gneiss-osity. Slaty cleavage is the foliation or texture that slate has. Slate is a metamorphic rock composed of individual mineral grains that are too small to see unless you magnify them. Slate splits easily along cleavage planes because of the way its crystals are formed. If you run your hand over a piece of slate, you may feel little ridges or bumps that tend to run parallel to each other. This foliated texture is slaty cleavage.
Schistosity is the term used to describe the foliation of schist, another type of metamorphic rock. Schist has individual mineral grains that are large enough to see without magnifying them. Over half of the minerals in schist are flattened and platy are elongated and rod-like in shape. There are different types of schist, and each type is known by its component mineral that lends the rock its most conspicuous characteristics. For example, biotite schist is distinguished by its dark bands of biotite mica.
The mineral composition of schist produces a texture called schistosity, or schistose foliation. Schistosity looks scaly and wavy. On the fresh surface exposed when the rock is split, it is clear that flattened, platy minerals are organized parallel to each other, with lighter and darker colored minerals segregated into distinct bands.
Hey, can I buy a vowel?
Gneiss-osity describes the characteristics of gneiss. Gneiss is metamorphic rock with large, granular minerals and visible light and dark bands that make the rocks look streaked. Gneiss breaks in an irregular pattern, and the segregation of minerals into light and dark bands is more prominent in gneiss than it is in schist. Isn't that nice?
At this point, we'd like to make you familiar with an old geologist's joke. Gneiss is usually formed when granite withstands the high heat and pressure of metamorphism. Because of the similarities between granite and gneiss, students of geology often mistake one for the other. Here comes the joke. It's a nice rock, but don't take it for granted. Pretty dumb, huh? But make every effort to use this one around your professor. You'll get big-time brownie points.
Metamorphic rocks that don't have foliation, lineation, and directional texture are called hornfels. The texture of hornfels is called hornfelsic or granular. Any flat or elongated minerals in these rocks are oriented randomly.
It's pressure that causes the minerals to line up parallel to each other in schist and gneiss. Hornfels usually form from contact metamorphism. In contact metamorphism, the metamorphosed rock is changed by the heat of an intruding magma, rather than from heat accompanied by tremendous pressure. Heat without the pressure metamorphoses rock, but it doesn't line the minerals up in a parallel fashion.
Let's take this opportunity to repeat some of the funny words we've learned so far. Pluton, cleavage, schistosity, gneiss-osity, and hornfels.
Here's what we've learned about metamorphic rocks. They're classified by their texture. The 2 main categories are foliated metamorphic rocks and hornfelsic or granular metamorphic rocks. Foliated metamorphic rocks include slate, schist, and gneiss. Each of these is characterized by one or a combination of these factors. Slaty cleavage, which means it can easily split along cleavage planes, and the planes often have bumpy parallel ridges. Schistosity, which is scaly foliation composed of large-grained minerals that you can see without magnifying them. And gneiss-osity, which is the coarsest foliation characterized by alternating bands of light and dark minerals. Hornfelsic, or granular metamorphic rocks, are characterized by coarse or fine interlocking minerals that don't align themselves in any particular direction or fashion. Are you familiar with
cross-cutting relationships?
Yes, I'm in one now.
Have you ever been cross-cutted?
Not that I'm aware of.
Neither have I.
Don't know anything about it. Red.
What would that be?
Well, that's kind of what I'm asking you.
Excuse me?
Here's how the rock cycle works. Sediments accumulate and form sedimentary rock. Buried and subjected to powerful forces, sedimentary rock will become metamorphic rock. If metamorphic rock is heated to extremely high temperatures, it will become magma, and cooled magma forms igneous rock. Along the way, any of these rocks may be weathered or eroded into sediment, starting the cycle all over again. It's pop quiz answer time. We asked, which of the following is not a primary cause of metamorphism in rocks? The correct answer is A, evaporation. Evaporation helps form sedimentary rocks, not metamorphic rocks.